Complex analysis can be one of the most unintuitive yet interesting areas of maths one might stumble across. The transition from a number system with ordering to the complex numbers which are unordered can be a bit mind-boggling. Despite its apparent unintuitiveness, however, the tools that complex analysis generates are used all over physics, from classical mechanics all the way up to quantum field theory. In this video, we'll have a look at an interestingly physical and intuitive result of a few concepts in complex analysis. One of the central ideas in complex analysis is holomorphicity. A holomorphic function is like an extension of a differentiable function to the complex plane. In particular, a holomorphic function obeys the criterion of the limit along the real and imaginary axes existing and being equal. If we let f be a holomorphic function and then decompose f into its real and imaginary parts, we can fairly directly derive what's called the Cauchy-Riemann equations. If a function obeys these relations, that function is holomorphic. Hold that thought while we move on to another idea. A harmonic function is a function where if you take the Laplacian of it, you get 0. In our next proof, we'll be using the Laplace operator in 2 dimensions, which is defined like so. Next, we need to prove that all holomorphic functions are also harmonic, meaning its real and imaginary parts are harmonic. We'll do this by showing that a holomorphic function obeys the Laplace equation. A holomorphic function f obeys the Cauchy-Riemann equations, so it can be rewritten like this. We let z bar be the conjugate of some complex z, and define x as the real part of this function and y the imaginary part. We can simply write our definition for x and take the derivative with respect to z bar. We do the same for y. Now we have a new expression for the derivative with respect to z bar, and we can just apply this to some function f. Remember our Cauchy-Riemann equations from earlier? What we have here will just go to 0. Now we have that the derivative of some function f with respect to z bar is 0. Next, we can take the derivative with respect to z of the derivative with respect to z bar of f. The derivative of 0 with respect to anything is of course 0. We can use the same process as earlier to get the derivative with respect to z. We end up with this result. Then we can simply apply this derivative to the one we had before and apply both to f. After multiplying this out, we quickly see that we've actually just produced the 2D Laplacian we talked about earlier. If a function obeys this relation, it must be harmonic. So we've proved that all holomorphic functions are made up of harmonic real and imaginary parts. Next, we can talk about some physical results. The continuity equation governs the transport of quantities and is given by this relation, where v is the velocity vector field and ρ is the density. Since water has constant density, we can simplify this equation when dealing with incompressible water flow. Then the velocity can be written as the gradient of some scalar field plus the curl of another vector field. Now let's prove that the scalar field, which we'll call the velocity potential, is harmonic. We already have, by the continuity equation, that the divergence of velocity must be 0, so we'll use that fact to continue. To prove this is harmonic, we must first prove that the divergence of the curl is always 0. To start, let's express the curl in terms of the Levi-Civita symbol. So we've proved that the Laplacian of our potential is 0. This is the Laplace equation we discussed earlier, so this function is harmonic. Now let's talk about the vector field component. We can define A as a vector potential perpendicular to the plane where the fluid flow is taking place, which we'll assume is the z direction for now. We'll call the psi we used to define A the stream function. Using an identity, we'll rearrange what we had before for a new way to express velocity. A conformal map is a holomorphic function that maps the physical domain of x and y to a new domain with phi and psi. We've just shown phi and psi are harmonic functions, so we can actually use conformal mapping to deal with problems in fluid flow. Now that we've defined this holomorphic map, we can use the Cauchy-Riemann relations to prove orthogonality between lines of constant psi and phi. We can do this by taking the dot product of the grad of psi with the grad of phi. Since the two are orthogonal, the result will be 0. Let's return back to complex analysis and look at the open mapping theorem. If f is a holomorphic function over domain D, the image of the subset under the function is also an open set. The maximum principle states, for any non-constant function f that's holomorphic on a closed set C, the maximum of the magnitude of f occurs on the boundary of the set, which we'll call delta C. This seems a little wordy, but it's actually really intuitive. Let's prove it. First, we have to say that there should be a maximum at all. We can do this using the extreme value theorem for the magnitude of the function f. This basically says, since the magnitude of f is continuous and maps a closed set to a closed set of real numbers, there exists a maximal and minimal value. So, now that we've declared that there must be a maximum point, let's prove that it can't be in the set and therefore has to be on the boundary. Let's define a generic holomorphic function f and assume that there's a point in our set where the function's magnitude is indeed maximized. We'll call this point x0. Then let's look at a small open disk of radius epsilon around this point. From the open mapping theorem, we know this disk will map to another open set. If we choose another point x1 closer to the boundary and take the magnitude of f at x1, visually it's clear that the magnitude of f at x1 is greater than it is at x0. This contradicts our original assumption that there exists a maximum point on the interior of the boundary. Then, since there must exist a maximum point, we can conclude that it exists on the boundary of the set. We've just proven the magnitude of a holomorphic function is always maximized at the boundary. This means the magnitude of the conformal map is also maximized at the boundary. Let's delve into this to figure out what it really means using water flow around a cylinder as an example. This diagram shows the streamlines mapped out, which are lines of constant psi. This is the path the fluid takes around the cylinder. It's clear that the cylinder can be defined as a boundary, given that the water doesn't intersect it at any point. So let's see how the fluid flow is maximized by looking at the boundary. Because water must go around the cylinder in order to flow forward, the velocity must change at the boundary. Since there's no other disturbances in the water in our case, the only place we could find maximum or minimum speeds should be the boundary. In actuality, this is what we see. The maximum speed in the flow is indeed on the sides of the cylinder. But how can we make sense of this mathematically? We know the magnitude of the conformal map will be maximized at the boundary. And although that gives us the correct intuition, that doesn't actually tell us anything concrete. Let's take a step back from the abstract ideal of conformal mapping and talk more about how we know physical parameters like speed will be maximized at the boundary. Multivariable calculus tells us the conditions at which we can find local extrema in a function. We can go ahead and define two separate scenarios for when we have a stationary point. The determinant of the Hessian D must be positive in order for there to be a maximum value at that point. Let's look at the Laplace equation that defines harmonic functions. The partial derivative with respect to x is of opposite sign to the partial derivative with respect to y. D will be less than 0, and the point assuredly is not going to be a local maximum. Now, this rough explanation doesn't account for the situation where D is 0, which is still a possibility. Now, we've seen how holomorphic functions are deeply connected to harmonic functions. In fact, we've proven that the real and imaginary parts of any holomorphic function are themselves harmonic. This becomes a powerful bridge between complex analysis and the physical world. In fluid dynamics, where harmonic functions describe potential flows, which are idealized, incompressible, and irrotational fluids, the tools of complex analysis allow us to model two-dimensional flow fields intuitively. The velocity potential and stream function are harmonic, and together they form a holomorphic function called a complex potential. The properties we discover in the study of complex analysis then get projected directly into our understanding of fluid flow. This connection between abstract maths and real-world phenomena is one of the reasons why complex analysis is so compelling. It shows us how complex functions, when viewed through the right lens, describe physics in a natural way. Thanks for watching. If you enjoyed this video or haven't seen some of these concepts before, we recommend watching our Real Analysis lecture series that discusses similar concepts.